Section 14.3, dependence of reactant concentration on time. So now we're going to look at the effect of time on reactant concentration. We can use the rate law to determine the rate of a reaction using the rate constant and the reactant concentrations. Rate law. Rate equals K times the concentration of A to the X times the concentration of B to the Y. The overall equation is called the rate law. The rate is also proportional to the rate constant, K. A rate law can also be used to determine the remaining concentration of a reactant at a specific time during a reaction. We will illustrate this use of rate laws using reactions that are first order overall and reactions that are second order overall. So we're going to just look at two examples. There are a multitude of possible arrangements of the rate law, but we're just going to look at two examples. First order reactions. A first order reaction is a reaction whose rate depends on the concentration of one of the reactants raised to the first power. Two examples are the decomposition of ethane, C2H6, into highly reactive fragments called methyl radicals, .CH3. That dot, by the way, very hard to see it. That dot just to the left of the carbon atom is a radical. It's a unpaired electron. And the decomposition of nitrogen, dinitrogen pentoxide, N2O5, into nitrogen dioxide, NO2, and molecular oxygen, O2. So here is the examples we're going to look at. C2H3 turns into two CH3s with a rate equal to K times the concentration of C2H6. That's first order. 2 N2O5 turns into 4 NO2 plus O2. Rate equals K times the concentration of N2O5. That is also first order. How do we know they're both first order? Well, people have determined it experimentally, so they've gotten that answer for us. But just by looking at the form of the rate law, you can tell. The fact that the exponent is not shown means it's a 1, right? And if the exponent is 1 and there's only one reactant in that equation, then that is first order. If it was squared, it'd be second order. If it was cubed, it'd be third order. In a first order reaction of the type A turns into products, the rate can be expressed as the rate of change in reactant concentration. So rate is equal to minus the change in the concentration of A over the change in time. Remember, that's from section 1. As well as in the form of the rate law. Rate equals K times the concentration of A to the first power. That's from section 2. Setting these two expressions of the rate equal to each other, we get minus change in concentration of A over change in time equals K times the concentration of A. Let me expand that a little bit so you can see it. Calculus. Applying calculus to the preceding equation, we can show that, equation 14.3. The natural log of the ratio, concentration of A in time divided by concentration of A 0 equals minus KT. So now there's some notation to go over. ln is the natural logarithm, and concentration of A0 and concentration of AT are the concentrations of A at times equals 0 and time t, respectively. In general, time 0 refers to any specified time during a reaction, not necessarily the beginning of the reaction. Time t refers to any specified time after time 0. Equation 14.3 is sometimes called the integrated rate law. Integrated rate law. And that's because it uses integration, a technique used in calculus, to figure it out. So that step where you're getting to equation 14.3 from the preceding equation right above it, if you don't know calculus, you don't know how they got there. If you do know calculus, it's a very, very simple process. But we don't have to go through the calculus here. It's right there. Equation 14.3 is what we'll use. So if you take a look at sample problem 14.4, that one right there will give you an example of how to use equation 14.3 to solve a problem, as will the practice problems A and B. Now, moving on. Equation 14.3 can be rearranged as follows. Equation 14.4. Natural log of the concentration of A in time is equal to minus kT plus the natural log of the concentration of A, 0. Okay? Equation 14.4 has the form of the linear equation y equals mx plus b. Remember, that's the equation for a line from your algebra classes. Natural log of AT equals minus k times t plus ln A naught. Y equals mx plus b. So y is the natural log of the concentration of A in time. M, the slope of a line, is equal to minus k, the rate constant. And x is time, and then the y-intercept b is natural log of A, 0. Student note, because pressure is proportional to concentration for gaseous reactions, equations 14.3 and 14.4 can be written as ln pt over p0 equals minus kT. So there they're just substituting pressures for concentrations. And ln pt equals minus kT plus ln p naught, again, substituting pressures for concentrations, respectively, where P0 and PT are the pressures of the reactant A at time 0 and time t, respectively. Figure 14.8a shows the decrease in concentration of reactant A during the course of the reaction. As we saw in section 14.1, the plot of reactant concentration as a function of time is not a straight line. For a first-order reaction, however, we do get a straight line if we plot the natural log of reactant concentration, ln AT, versus time, y versus x. The slope of the line is equal to minus k, figure 14.8b. So we can determine the rate constant from the slope of this plot. Student note, this graphical determination is an alternative to using the method of initial rates to determine the rate value of k. So in other words, we're going to use this method as a different method compared to the previous section. Section 14.2 talked about the method of initial rates, right? So we're going to do a different method to find the same information. So there's our two figures. Look what happens to the concentration of A. It's decreasing in a curve. But if you take the natural log of the concentration of A and plot it versus time, you get a straight line. The straight line has a slope. The slope is equal to minus the rate constant. So if you can figure out what the slope is, you can figure out the rate constant. There's also a y-intercept. The y-intercept is the value of y when x is equal to 0. Well, when time is 0, it would be the natural log of A. We generally aren't as concerned about the y-intercept. We generally want the slope so that we can find the rate constant k. So the first order reaction characteristics. A, decrease of reactant concentration with time. B, a plot of ln of the concentration of A versus time. The slope of the line is equal to minus k, and the y-intercept is equal to the natural log of the initial concentration of A. Sample problem 14.5 shows how a rate constant can be determined from experimental data. You definitely want to take a look at that sample problem, as well as the practice problems that come along with it. Now here we're going to move into the idea of half-life. For those of you who are interested in the medical field, half-life is important, particularly with pharmaceuticals, with drugs. We often describe the rate of a reaction using the half-life. The half-life, expressed as T1/2, subscript 1/2, is the time required for the reactant concentration to drop half its original value. We obtain the expression for half-life, T1/2, for a first-order reaction as follows. T equals 1 over K, remember K is the rate constant, times ln A0 over AT. According to the definition of half-life, T equals T1/2 when AT is equal to 1/2 A0. In other words, when the concentration of A is 1/2 of its initial concentration. That's how we're defining it. Let's go back to that definition. The half-life is the time required for the reactant concentration to drop to half its original value. So, according to the definition of half-life, when T1 half AT equals 1 half A0, T1 half would be 1 over K times ln of A0 over 1 half A0. Because A0 over 1 half A0 equals 2, and ln2 equals 0.693. By the way, you want to do that in your calculator. Take your calculator, put in ln of 2. Your calculator will either do it as you put the 2 and then hit ln, or you'll hit ln and then hit 2 equals. It should be equal to approximately 0.693. The statement that it is equal to 0.693 is not true. It is approximately equal to 0.693. For any calculation that you're doing, you're perfectly fine using that value, ln2 equals 0.693. The expression for T1 half simplifies to equation 14.5. T1 half equals 0.693 over K. All right? Look at that simple equation. T1 half equals 0.693 over K. That's about as simple as it gets. All that derivation leads you to this. If for a first order reaction, the half-life is nothing more than 0.693, which is the natural log of a half, divided by the rate constant. You'll be able to do all sorts of calculations with that very simple equation. According to equation 14.5, the half-life of a first-order reaction is independent of the initial concentration of the reactant. Thus, it takes the same time for the concentration of the reactant to decrease from 1 molar to 0.5 molar as it does for the concentration to decrease from 0.1 molar to 0.05 molar. In other words, just going down by half, it doesn't matter what the initial value is, going down to a half is going to have the same half-life. Measuring the half-life of a reaction is one way to determine the rate constant of a first-order reaction. Why? Look at that equation. If you know what the half-life is, you can very simply rearrange equation 14.5 and figure out what K is. Here's figure 14.9, a plot of the concentration of A versus time for the first-order reaction A turns to products. The half-life of the reaction is 1 minute. The concentration of A is halved every half-life. So every half-life, the concentration of A goes down a half, 50%. You're really going to have to get practiced at thinking of what does a half mean. A half is 50% of what you started off with, or 0.5 of what you started off with. The half-life of a first-order reaction is inversely proportional to its rate constant, so the short half-life corresponds to a large rate constant. Consider, for example, 2 radioactive isotopes used in nuclear medicine. Sodium-24, which has a half-life of 14.7 hours, and cobalt-60, which has a half-life of 5.3 hours. Notice the half-lives are in time units, but they could be different time units, minutes, seconds, hours, years. Sodium-24 with the shorter half-life decays faster. If we started with an equal number of moles of each isotope, most of the sodium-24 would be gone in a week, whereas most of the cobalt-60 would remain unchanged. Think about why that's true. Look at those half-lives. Sample problem 14.6 shows how to calculate the half-life of a first-order reaction given the rate constant. Now we're going to move on to second-order reactions. A second-order reaction is a reaction whose rate depends on the concentration of one reactant raised to the second power, or on the product of the concentrations of 2 different reactants, each raised to the first power. For simplicity, we will only consider the first type of reaction. A turns to products, where the rate can be expressed as rate equals minus concentration of A, change in concentration of A, I should say, divided by change in time. Or as rate equals K times the concentration of A squared. As before, we can combine the 2 expressions of the rate. Minus change in the concentration of A over the change in time equals K times concentration of A squared. Again, using calculus, we obtain the following integrated rate law. 1 divided by the concentration of A in time equals KT plus 1 over the initial concentration of A. That's equation 14.6. That equation is useful. Thus, for a second-order reaction, we obtain a straight line when we plot the reciprocal of concentration 1 over AT against time. And the slope of the line is equal to the rate constant K. As before, we can obtain the expression for the half-life by setting AT equal to 1/2 A0. 1 over 1/2 A0 is equal to KT 1/2 plus 1 over A0. Solving for T 1/2, we obtain T 1/2 equals 1 over K A0, equation 14.7. That's the half-life. So equations 14.6, 14.7, those are the results. Those are the equations you can use to do calculations for second order. Again, figure 14.10, second order reaction characteristics. Decrease of reactant concentration with time. Notice it's nonlinear. Concentration of A versus time, that's figure A. Figure B, 1 over concentration of A versus time. Notice that is linear, straight line. Slope equals rate constant K. A plot of 1 over AT versus time. The slope of the line is equal to K, and the y-intercept is equal to 1 over A0. Note that unlike the half-life of a first-order equation, or reaction, I should say, which is independent of the starting concentration, the half-life of a second-order reaction is inversely proportional to the initial reactant concentration. Determining the half-life at several different initial concentrations is one way to distinguish between first-order and second-order reactions. Sample problem 14.7 shows how to use equations 14.6 and 14.7 to calculate reactant concentrations and the half-life of a second-order reaction. Sample problem 14.7. First and second-order reactions are the most common reaction types. Reactions of overall order 0 exist, but are relatively rare. For a 0th order reaction, A turns to product, and the rate law is given by rate equals K times the concentration of A to the 0 equals K. So rate just equals K, it's constant. Thus, the rate of a 0th order reaction is a constant, independent of reactant concentration. Third order and higher order reactions are quite rare and too complex to be covered in this book. Good for us, right? Table 14.5 summarizes the kinetics for first order and second order reactions of the type A turns to product. So look at table 14.5, and what you'll see is there's a summary of kinetics of 0 first order and second order reactions. The rate law is given, the integrated rate law is given, as is the half-life. Now we're up to the checkpoint for section 14.3. Of course, you want to do the checkpoint problems as well. And that ends this section.